Okay, good day. So today we're going to do some circuit examples to finish up the circuit chapter. So I have four examples in mind, and I'm not necessarily going to do them in order. I've already written them down, one, two, three, four. And I'm going to start with number four. So circuit number four is a straightforward parallel circuit. So in this parallel circuit example, I'm asking what is the potential difference in current everywhere in the circuit if R1 equals R2 equals 3 ohms, and then if they're different from each other. So to start with, let's go ahead and analyze this circuit. We can do Kirchhoff's loop rule, or just use the fact if we remember that in parallel, everything that's in parallel with each other must have the same potential difference. You can use Kirchhoff's loop rule to show that, but that is a result of Kirchhoff's loop rule, that therefore the potential difference across R1 must equal the potential difference across R2, must equal the potential difference across the battery, must equal 9 volts. That's, again, due to Kirchhoff's loop rule, or due to the fact that, therefore, things in parallel must have the same potential difference. So that is the potential difference everywhere. And then if we know the potential difference everywhere, if we know the potential difference across R1 is 9 volts, that is equal to the current through R1 times R1. So therefore, the current through R1 is 9 volts over 3 ohms, which is 3 amps. And again, by symmetry, or by the same kind of argument, therefore, the potential difference across R2 is also 3 amps. It's the same resistance, it's in the same position, so it's got the same current. That's A. What about B? In B, we've still got that the potential difference across R1 is equal to the potential difference across R2, is equal to the potential difference across the battery, is equal to 9 volts. That's the potential everywhere. So now what about the current? Let's just think qualitatively. Qualitatively, the smaller resistor will have larger current. So there's two ways to do this. One is to apply Kirchhoff's rules directly. Another is to think about it from a equivalent circuit point of view. So applying Kirchhoff's rules directly, we can go ahead and say delta V across R1 is equal to I1, Kirchhoff's rules and Ohm's law, I should say, and Ohm's law. Delta V across R1 is I1 R1, therefore I1 is equal to delta V over R1, which we already did that before, but now it's 9 volts over 2 ohms, which is 4.5 amps, and therefore by the same argument, I2 is 9 volts over 4 ohms, which is 2.25 amps. If we want to just look at that from an equivalent circuit point of view, the equivalent circuit is, I'm just going to talk this through. So in the lower right-hand corner, the equivalent circuit is drawing the same circuit with a single resistor, and that single resistor must have an equivalent resistance of, we're going to add 1 over R equivalent is 1 over 2 plus 1 over 4, so taking the inverse of that. The equivalent resistance is 4/3 of an ohm. This is a much harder way of actually solving this problem. Using the equivalent resistance of 4/3 of an ohm, we can then figure out, and I'm just going to talk this through, I'm not going to write it out. You can figure out that, therefore, the current coming from the power supply is equal to 9 volts divided by 4/3 of an ohm, which is going to be 6.75 amps. Then we know that we have 6.75 amps, and that is going to be divided in a 2-to-1 ratio between the resistors, and hence we end up with these numbers here. That's a conceptual way of seeing how to use equivalent circuit, but it's actually a harder way. Okay, that's example number 4. Again, we're doing them out of order. Here I've got example number 3. I'm going to ask the same question for 2 resistors in series. What is the current? Oh, wait a second. Did I do? Yeah, I did everything on the other one. What is the current and potential difference everywhere if R1 equals R2 equals 3 ohms, and if they're not equal to each other, if they're 2 and 4 ohms? So here, again, we can just use Kirchhoff's rules and Ohm's law. But you can, again, use arguments that are results of Kirchhoff's rules and Ohm's law that we've seen before, conceptual arguments. Like, for instance, if the resistors are the same and they're in series with a power supply, then they are going to share the the voltage or potential difference equally. So by that argument, the answer to part A for the potential difference is that they've got 4.5 volts each. We can go ahead and show that using Kirchhoff's loop rule, that if we start, let's say, at that point in the circuit and we go around that way using Kirchhoff's loop rule, we're going to have plus 9 volts, and we're going to assume I should have drawn in the current first. If the current goes in that direction, then we're going to have minus IR1 minus IR2. The current in each is the same because we're in series, there's no branches, equals 0. As we go around the loop, that is Kirchhoff's loop rule. So therefore, sorry, hold on. This is an indirect, I just realized that I'm going to calculate the current first. It's an indirect way of getting to the potentials, but we're just going to calculate the current. So therefore, 9 volts equals I times R1 plus R2, and which is I times 6 ohms. And so therefore, I is 9 over 6 amps. And so then we can go ahead and say, therefore, delta V R1, delta V R1 is equal to I1 R1, and that is 1.5 amps times 3 ohms, which is 4.5 volts, and delta V R2 is I2 R2, which is 1.5 amps times 3 ohms, 4.5 volts. Okay, so we found the current everywhere, and we found the potentials everywhere. You did have to recognize that there is just one current in this circuit, and nothing else. Okay, so that's what we recognized. That's what we calculate. Okay, so what if the resistance... Oh, I know what I was going to say. Yeah, so we could also use the concept of equivalent resistance. The equivalent resistance of this circuit in part A is R1 plus R2. They're in series, so it's 6 ohms. And so from the concept of equivalent resistance, 6 ohms, we can immediately see that the current pulled from the battery must be not the potential of the battery divided by the current of the battery is equal to the equivalent resistance. So we can, from equivalent resistance point of view, we can say delta V of the battery divided by the current of the battery is equal to the equivalent resistance of the circuit. And so from that, we can see that 1.5 amps. If the equivalent resistance is 6 ohms, then 1.5 amps must be pulled. And so we immediately get to, without doing Kirchhoff's loop rule, we immediately get to the current is 1.5 amps. Once we know the current is 1.5 amps, we can figure out the potential due to across each resistor, which is the current through the resistor times the resistance. Okay, let's do part B. Part B, by the same argument that we just made, if the total current is, the equivalent resistance is still 6 ohms, then the potential, if the equivalent resistance is still 6 ohms, then the current is still 1.5 amps. Or the equation that we wrote down, this is still true, right? This is still true for part B. Now R1 and R2, so we're still going to get 1.5 amps. Then delta V, this is still true, and the only difference is the resistance here. So delta V, the potential difference across R1 is 1.5 amps times 2 ohms. I'm not going to write this down. Is therefore 3 volts, and the potential difference across R2 is 1.5 amps times 4 ohms, which is 6 volts, right? So it's going to be 3 volts and 6 volts. So for part B, it's going to be 3 volts. Well, let's find a way to write this. There, I just wrote it down. So for A and B, there's the same current. For part B, it's 3 volts across the smaller resistor and 6 volts across the bigger resistor. Okay, that's 2 down, 3 to go. I can't remember how many I said I had, but I have 5 examples. Okay, let's see, which example do I want to do next? Let's go ahead and do this slightly more complicated example. Basic circuit. This is a basic circuit, but just a little bit more complicated. So now I've got 3 resistors. not necessarily in series or in parallel. So far, we've just been doing just series or just parallel. And actually, I want you to look at these resistors and just tell me, this is not a question I had asked, but I guess I could ask, are any of these resistors in series or in parallel with each other? In the end, you can pause it and think about it, but otherwise I'll say R1 is not in series with R2 because there's a junction between R1 and R2, and that's the same with R2 and R3 and R3 and R1. There's a junction between, so none of these are in series with each other. Are either of them in parallel with each other? Well, let's just think about what it means to be in parallel, right? Is R1 in parallel with each other? In other words, are the two wires coming out of R1 attached to the same attached to the two wires coming out of anything else? And the answer is no, it's not. It is not in parallel with anything. Are the two wires coming out of, let's draw them in a different color. Are the two wires coming out of R3 attached to the same two wires coming out of something else? I keep saying same two wires. And then that's a little harder to see, but the answer is yes, because R3, here's one wire, here's the second wire, and R2, let's draw them there and there. The two wires coming out of R2 are attached to the two wires coming out of R3. So R2 and R3 are actually in parallel. That doesn't actually matter. It might help to understand what's going on in this circuit. It might help to take some shortcuts, but we don't need to know that in order to do this problem. Okay, so let's go ahead and ask, what is the current everywhere? So what we really should do, and I haven't always been doing this, is when we're asking these questions about what is the current everywhere, what is the potential difference everywhere, we should draw in the currents. So we have a current coming out of the battery. Let's call that I1. That current is going to split at the junction between R1, R2, and R3. And so let's call the current going up this way I3, and the current going to the left through R2, we'll call that I2. Again, if you choose a different direction, that's okay. We'll just find that if you're wrong about the direction, that it's negative. But think about current like water flowing. We haven't really talked about that analogy, but current is like water flowing. If water is flowing from the plus plate of the battery, from the big plate of the battery, and it gets to this junction, it's going to keep flowing through the junction up and to the left. And then when it gets back to the junction on the left, right, I3 is still coming around the top, right? I3 is coming around the top, I2 is coming to the left, and they combine, and this better be I1 because the battery does not use up current. The current has got to be the same everywhere along a wire, through even when it goes through something, right? The current only changes at a junction. Current only changes at a junction. Okay, whoops, this was I3. Okay. So from Kirchhoff's junction rule, the junction rule tells us that I1 is equal to I2 plus I3 because at either of the junctions, we've got I1 on the right coming in and I2 and I3 going out. On the left, we've got I3 and I2 coming in and I1 going out. So we've got three unknowns, so we've got to have at least two more equations, and we're going to do the loop rule. So first we did the junction rule, and we are solving for A. Well, we're going to really do A and B at the same time, but now the loop rule. So what I'm going to do is, again, you can start anywhere, but I'm going to start at the power supply and do counterclockwise around the bottom. Counterclockwise around the bottom, meaning the loop rule, I'm going to say if we go from the minus plate to the plus plate of the potential difference, we call it plus delta V, and then we're following the current through the resistor, so the resistor uses up potential energy, so we've got minus I1 R1, and again, I'm doing the bottom loop, not the whole big loop, and then we're, again, following the current through R2, so we've got minus I2 R2. That's the following the current. If we're in the direction of the current, it's a minus sign when we go through a resistor. If we're opposite direction of the current, it's a plus sign. And then we come around back to the battery, and so we got 0. So now we've got two equations. We still have three unknowns, right? The I1, I2, and I3 are unknown. So let's do another loop. And actually, just to do something different, let me do the top loop, right? So this is the bottom loop. let's do the top loop, meaning R2 and R3. So the top loop, and let's go ahead and start right there, right? We're going to start at that junction on the left, and we're going to go counterclockwise. So I'm going to first pass through R2, but I'm going opposite the current. So because I'm going opposite the current, we're getting a gain in potential difference. So we're going to get plus I2R2. And then I follow counterclockwise around the top loop. And so now I'm following the current I3 through R3. So I've got minus I3R3. And then I come back around and I've done a full loop. I come back around to where the yellow arrow started and I get 0. So that's the top loop. And both of those loops I did counterclockwise. Okay, so now I've got 3 equations, 3 unknowns. Now I should be able to solve for current everywhere. Once I know current everywhere, then I should know be able to find potential difference everywhere. Remember, we got to keep in mind what we know and what we don't know. We know the resistors and we know the potential differences. So the unknowns are I1, I2, and I3, right? Those are the unknowns. We know everything else. We know the resistances and the potential differences. So I'm going to go ahead and do this algebra on this page. It's algebra, so I'm not going to necessarily talk you through it. What I'll do is I'll write it out. You can look at it, and you can stop the video and see if you can follow the steps. But this is algebra that hopefully you can solve for I1, I2, and I3. But I'll tell you the basic steps that I'm going to do. It's what we call the basic plug and chug. We're going to take the first equation and we're going to solve for I1. It's already solved for. We're going to go ahead and plug I1 into the second equation. So then we've only got I2 and I3. And those 2 equations, the third equation is only I2 and I3 also. So then we'll take one of those 2 equations and solve for I2 and then plug in so we have only I3. Okay. So I went ahead and did that algebra and I end up getting I2 is this expression over here. This expression over here. Okay, so did the algebra. Sorry, I took a time off, so I'm not sure where I was. But I did the algebra by brute force plug and chug, solving for I1, then solving for I3, then solving for I2. By plugging each equation successfully into the next. And so then what I got was I2 is a relatively big expression, and then I plugged in the numbers. Delta V is 12 volts, and R1, R2, R3 are all 10 ohms. So that gives us 0.57 amps for I2. Then we go ahead and we can use I2 to find I3. Since R2 and R3 are the same, then I2 is equal to I2 is equal to I3, so I3 is 0.57 amps. And so then we can go back to the original equation. I1 is the sum of I2 and I3, so I1 is 1.14 amps. So I1 is 1.14 amps. Once we've got those 3 currents, we can go ahead and go back and figure out, if we know what R1, R2, and R3 is, we know what the potential difference across each is. So let's go back and say, okay. Since the current I2 is through R2, then the potential difference across R2, which is 10 ohms, is 5.7 volts. The potential difference across R3, because it's got I3 going through it, and it's 10 ohms, right? Potential, I'm just using the lower left-hand corner, I'm just using the potential difference across the resistors, the current through the resistor times the resistance. So the potential difference across R1 is 11.4 volts, and the potential difference across R2 is 5.7 volts, and the potential difference across R3 is 5.7 volts, just multiplying each current by the 10 ohms. Okay, so then the question is let's just check and make sure this all makes sense. And hint, it doesn't. So first of all, the current coming out of the battery goes through R1 and then splits. Because R2 and R3 are equal, it should split equally. We probably could have seen that I2 and I3 are the same. And that is indeed true. And R1 is the sum. The current through R1 is the sum. So the relationship between the currents makes sense. But the potential differences, there's something wrong. I recognize as soon as I wrote them down on this page. And by the way, I put the solutions at the bottom in black. And that is that R1, the potential difference across R1 plus the potential difference across R2 should equal the potential difference of the battery, which is 12 volts. And it only does approximately, and so that could be a rounding error. But then the one loop that we didn't do, the big loop, the potential difference across R1 plus the potential difference across R3 should equal the potential difference across the battery, and it doesn't. That equals 17 volts, but delta V1 plus delta V3 is 17 volts, which is bigger than 12 volts. So it seems like I made a error somewhere in the amount of current. So what I'm going to do is, while the basic solution process was correct, I'm going to correct that, and we have 2 or 3 more examples that I'm going to do in class tomorrow. So we'll finish up for today. I'll fix the algebra for tomorrow and then do the last couple examples.